Hi, I'm Ainesh Bakshi, and I'll be talking about a new approach to learning a linear dynamical system. This is based on joint work with Alan Liu, Ankur Moitra, and Morris Yao. Before we dive into what a linear dynamical system is, I want to state the overarching theme of this work, which asks whether we can use the algorithmic toolkit developed in TCS for statistical estimation tasks to analyze time series data. Crucially, in this setting, the underlying statistical process is correlated across time steps, making it harder to use existing techniques. So why should we care about time series data? Well, it's ubiquitous across applications in physics, control, navigation, robotics, finance, scientific computing, and so on. With that theme in mind, let's dive into defining a linear dynamical system, where the dynamics essentially evolve linearly over time. Formally, we have a state vector, x, and at time t plus 1, it is obtained by multiplying a matrix A, called the dynamics matrix, with the state vector at time t. Additionally, we add a control vector u sub t, which is typically something we get to design. The point of the control vector is to inject signal into the system instead of just letting it evolve on its own. The control vector is scaled by the control matrix denoted by B. Finally, we add process noise Wt, which is typically unknown and can be used to model various physical phenomena. This completely defines how the state evolves over time, given some initial conditions, which we'll ignore for the purposes of this talk. There is one final twist. Instead of actually observing the state vector x, at any time step t, we observe a potentially low-dimensional projection y sub t, which is obtained by multiplying x with the sensor matrix C. Note that C can have much fewer rows than columns, and in fact, C could just be a row vector. We then add in another copy of the control vector u sub t and multiply this by the matrix t, and we also add in observation noise denoted by the vector z sub t. So this defines the whole model. All right, now that we have defined the model, which you can see in the box on the right over here, let us state the problem of learning a linear dynamical system. Here, the input is a single trajectory of length capital N, which consists of pairs y sub t, u sub t, where recall the u sub t's are the control vectors and y sub t's are the observations. The goal is to learn the dynamics matrix A, the control matrix B, the sensor matrix C, and the matrix D from these yt ut pairs. In the setting that we consider, we are only given one long trajectory, and we cannot restart the dynamics to obtain a fresh copy. As stated, the problem is a bit ill-posed due to the symmetries present in the definition of the linear dynamical system. Even information theoretically, we cannot hope to recover the matrices A, B, and C exactly from just the observations y sub t and the control input u sub t. But we can only recover them up to an invertible transform u. This is because the observations do not change if we apply an invertible transform to A and then the inverse of this transform to B and C, and so on. So more formally, our goal is to output estimates hat A, hat B, hat C, and hat D such that they're close to the input matrices A, B, C, and D up to some unknown invertible transform U. The notion of error that we use is Frobenius error, and we want to recover estimates up to Frobenius error epsilon. To get some intuition about this problem, let's consider some natural settings of parameters and figure out when learning is possible. To begin with, let's consider the setting where the C matrix is the zero matrix. Then we never observe any signal since the xt term is always zeroed out. So we cannot hope to learn the dynamics A in this setting at all. More generally, consider the case where A is low rank and C projects away from the column span of A. Since the vector A times xt is always in the column span of A and C projects away from this subspace, we again do not observe any signal. And therefore, it's impossible to learn the parameters in this setting. Therefore, it's not hard to see that the matrices C and A must interact non-trivially. We can consider a similar example where B projects away from the span of A, and we cannot control the system at all by tweaking the U sub t's. Therefore, the U sub t's are playing no role in this setting, and it's easy to see that the matrices A and B must also interact non-trivially. This characterization of learnability was already formalized in the pioneering work of Rudolf Kalman in the 60s, and he gave these two definitions of observability and controllability that ensure that the matrices A and C and A and B interact non-trivially. Let's begin by defining observability. Here, consider the following matrix. We start off with the matrix C, and stack below it the matrices C times A squared, and so on, all the way to C times A to the S for some integer S. The underlying dynamical system is observable if this matrix has full rank. Similarly, Kalman also defined controllability. The linear dynamical system is controllable if the corresponding matrix here, where you start off with B and then stack along the columns A times B, A squared times B, and so on, is full rank for some integer S. Now, folklore theorem in control says that observability and controllability are information theoretically necessary, and they're also sufficient if we do not worry about sample complexity issues. However, the question that we are interested in this talk is the non-asymptotic complexity of learning a linear dynamical system. In particular, we want to characterize the minimal assumptions under which it is possible to learn a linear dynamical system efficiently, both in terms of sample complexity and running time. So what is known about this? Well, there's a long and rich body of work on the non-asymptotic complexity of learning a linear dynamical system spanning several decades. Sample-efficient algorithms are known as in various restrictive settings. And in practice, people typically use expectation maximization, but the maximum likelihood estimator becomes highly non-convex when the sensor matrix C is not the identity matrix. That is, you do not observe the state entirely. Existing sample-efficient algorithms can be mainly categorized as follows. One set of results assume that the linear dynamical system is fully observable, that is, the sensor matrix C is the identity matrix. Here, we know efficient, as in polynomial time algorithms, to learn the underlying dynamics. In the partially observed setting, there are numerous works that either make exotic assumptions about the eigenvalues of the matrix A, or assume that the eigenvalues are sufficiently smaller than 1, and the system is in the rapid mixing regime. When the system mixes rapidly, we can essentially forget about correlations across time steps and have access to nearly independent samples. Finally, there are also a set of works that work in the regime where the size of the linear dynamical system is a small constant, and the algorithms are exponential in the size of the linear dynamical system. In the next couple of slides, I'll state the assumptions in a bit more detail. I'm going to only flash through these slides, so feel free to pause the video and read the assumptions in detail or refer to the paper. All right, next, in the rapid mixing setting, existing works preclude systems with long-range correlations. The sample complexity and running time bounds that are obtained in these works scale inversely proportional to the spectral gap. This is an issue when the dynamics matrices are obtained from physical laws, which result in typically upper triangular matrices A, where the spectral gap is actually 0. since the largest eigenvalue is 1. Similar dynamics matrices are also obtained in many other applications, including discretization of ODEs, oscillatory systems, etc. Finally, the last class of algorithms that have been considered in prior work in the low-dimensional regime, where either the UT or YTs are scalars, or there's an exponential dependence on, say, the largest Jordan block, and so on. This motivates the following natural question. Does there exist an efficient algorithm to learn a high-dimensional linear dynamical system under essentially minimal assumptions? The main takeaway of this work is answering this question in the affirmative. There indeed exists an algorithm that requires a polynomial-sized trajectory and runs in fixed polynomial time under essentially minimal assumptions. I'll now spend some time discussing what these assumptions are. We know from earlier that observability and controllability are necessary. In particular, these matrices, as we considered earlier, need to be full rank. We soup up this assumption to say that these matrices have bounded condition number. I'd like to note that this is not a bait and switch on being minimal. We actually show that the condition number bound is in fact necessary. We also require that the system is non-exploding. That is, the largest magnitude eigenvalue of A is at most 1. It's crucial that we distinguish between the boundedness of eigenvalues and singular values. For instance, the dynamics matrices obtained from Newtonian mechanics actually have singular values that are much larger than 1, even though the eigenvalues are bounded by 1. For a simple example, consider the matrix A, where you have 1 and 1/2 on the diagonal and 1,000 on the top right entry. The largest magnitude eigenvalue of this matrix is 1, but the largest singular value of this matrix is 1,000. Next, we assume that the process noise WT and the observation noise ZT have bounded variance. This is actually a significant weakening of assumptions in prior work, which assume these noise distributions to be sub-Gaussian. Finally, we assume that the distribution of the control input is hypercontractive. The precise definition of hypercontractivity is not too important for the purposes of this talk. This condition essentially says that the fourth moment of the distribution is well-behaved, which is a strengthening of just the variance being bounded. This condition is satisfied by several well-studied distributions, including all log concave, sub-exponential, and sub-Gaussian distributions. I'd like to note that this is also a significant weakening of the assumptions required by all prior works, which assume that the control input is actually sub-Gaussian. One quick disclaimer here, we do not actually show that hypercontractivity of the control inputs, the use of these, is necessary. It is an interesting open question to either relax this assumption or show that this is necessary. I'll now formally state the main algorithmic result we obtain, given a trajectory of length at least n0 from a well-behaved linear dynamical system, which satisfies the assumptions that we discussed in the previous slide. There exists an algorithm that runs in time, which is polynomial in the number of samples, and the desired accuracy 1 over epsilon, and outputs estimates hat A, hat B, hat C, and hat D, such that with constant probability, the estimates are epsilon closed in Frobenius norm to the true parameters up to an unknown invertible transformation u. And this algorithm succeeds whenever the number of samples is at least a fixed polynomial in the size of the dynamics matrices, the sensor and control matrices B and C, the desired accuracy 1 over epsilon, the condition number of the observability and controllability, which is bound by kappa, and the variance of the noise, which is sigma. To complement this result, we also present a lower bound that shows that if the observability matrix has a condition number that scales like 1 over delta, then any algorithm that observes a trajectory of length little o of 1 over root delta cannot obtain even a constant approximation to the underlying parameters. Therefore, the sample complexity of this problem must indeed grow as a function of the condition number of the matrix. This result establishes a neat connection between learning a linear dynamical system and super resolution, which is where the hard instance is coming from. And if you'd like to know more, check out the paper. In the remaining few minutes, I'm going to describe some technical aspects of our result. I won't have time to go too much into detail, but this will serve as a primer for reading the technical overview section in our paper. At a high level, the algorithmic blueprint we follow is to try to estimate this matrix called the Markov parameter matrix. This matrix considers of stacking together the matrices D, B times A times B, C, A squared B, and so on. If we have a good estimate of this matrix, we can run the canonical Ho-Kalman algorithm to recover the individual parameters A, B, and C. This corresponds to solving a generalized eigenvalue problem on the matrix H as defined here. Note that the blocks appearing in H can be constructed from the blocks that appear in the Markov parameter matrix. So for our purposes, it suffices to estimate the Markov parameter matrix itself. Let's begin with a simple observation, which is that obtaining unbiased estimators of the Markov parameter matrix is easy. In order to do this, consider the cross-covariance matrix of the t plus jth observation, y sub t plus j, and the tth control, u sub t. It's not hard to see that if we average over such copies, then the resulting matrix is precisely C times A to the j minus 1 times B, which is an entry in the Markov parameter matrix. I'm going to quickly sketch a proof of this, expanding the definition of y sub t plus j. By unrolling the recurrence, we get an expression of this form. Right multiplying this expression by u sub t transpose, we can break the sum into 3 terms as described here. Taking expectations on both sides, we can see that the covariance of the UTs, when the UTs are distinct, is 0. So if I have u sub t plus j minus I times UT transpose, the expectation of this term is 0 since the UTs are independent. The only non-zero term here is when the UTs are the same. And when this happens, the corresponding expectation results in the identity matrix. Therefore, we're just left with C times A to the j minus 1 times B. The key challenges to make the above strategy work is that the samples are correlated. So for instance, for directions that have eigenvalue 1, there is no decay of correlation across time steps. This causes the variance of the aforementioned estimator to grow as a function of the time steps. The new ingredients that we introduced in this work involve transforming the observations y sub t's to hat y sub t's such that the following properties hold. The expectation of the new observations, the expectation of the cross covariance of the new observations is still C times A to the j minus 1 times B, and the variance of this estimator is still bounded. We find this linear we show that this transformation is linear, and we find this in a data-dependent way by solving a convex program. We prove that in the transform space, the observations do not have any long-range correlation, and therefore we can average over nearly independent copies and obtain an accurate estimator. For further read details, I refer you to the technical overview of our paper. I'm going to end by showing this slide on future directions. Feel free to pause and read through them. Thanks for tuning in.